Hello, everyone. I'm Raluca. I'm a computer science professor at UC Berkeley, specializing in privacy-preserving technologies, and I'm also co-founder and president of Opaque Systems. In this talk, I'll tell you about our open source framework, MC², which enables healthcare organizations to put their sensitive data together and learn from it jointly, while in the process also preserving the privacy of the data. And we released MC² as an open source from our lab at UC Berkeley. Here's why we need collaborative learning. Healthcare organizations, as you know, have a lot of private patient data. If they could put it together, then they could train better models for better diagnosis of diseases and better treatment of diseases. Because, well, they have complementary data, such as data from different geographic regions. For instance, we know that from year to year, flu prediction and the incidence of flu depends quite a bit on zip code. Or by putting their data together, they can have more data, which is especially important for rare diseases, such as rare forms of cancer, where one healthcare organization doesn't have enough data, but more organizations together can see more patterns as to what treatments worked well and what treatments didn't work well. But then you also know that a big problem is that healthcare organizations cannot easily share this data. This is because of privacy regulations, fear of losing control over how the data will be used, or even competition between healthcare organizations because they invested a lot of money perhaps in creating some data sets. And besides the healthcare use case, there's many other use cases where you want to do collaboration on private data, such as in the financial sector, or even nuclear facility auditing, or cloud-based video analysis in the cloud. This is why my students and I have been working for a number of years doing research on MC² to enable such collaborative learning in a private and secure way. MC² stands for multi-party collaboration and competition. And it embodies the principle that we should be able to share without showing the data. We should be able to put it together and compute and learn from it, but without actually showing it. And that might sound counterintuitive, but it's possible using the latest security and cryptography technology that I will mention. As I mentioned, this is open source under a permissive license, so you can play with it or use it in your settings. So let me tell you at a high level how this technology works. The idea is that each healthcare organization encrypts their sensitive data set, and then they put it together, maybe in a cloud or maybe on the premise of some organizations. Now, this data is encrypted, so nobody can see each other's data set. At the same time, they can compute jointly on this encrypted data. And we will see in a moment how. But the latest technology in crypto and security enables that. And during this computation, nobody gets to see each other's data. Not even the cloud gets to see the data of an organization. And the only thing that outcomes from the computation is the final result of whatever they wanted to compute. For example, it could have been training a model for cancer prediction. So that model outcomes from the computation. Now, how do we exactly do this computation? How do we exactly do this training on encrypted data? And today's state of the art has two different approaches. And we do research in both of them in MC², and our open source supports both of them. One is entirely cryptographic, which uses tools such as secure multi-party computation or homomorphic encryption, about which you might have heard. And the other is with hardware enclaves. I'll tell you a little bit about each one of them at a high level to give you a sense of how they work. And then I will compare and contrast these two approaches and discuss their pros and cons. Here's how the cryptographic approach works at a high level. Each healthcare organization encrypts its data and sends encrypted data to another organization. Again, this is encrypted data that's being transferred, so nobody can see and learn the data set of another healthcare organization. But the encryption scheme is such that it permits computation. There are such encryption schemes like homomorphic encryption schemes that permit computation on the encrypted data without decrypting the data. And manipulating the encrypted data, you essentially manipulate the underlying unencrypted data, but without decrypting. So then each organization uses this special function of these encryption schemes to be able to compute on encrypted data, and then they exchange more data and they do more computation. They keep repeating this process until the end, when out comes the function f that they all wanted to compute on their data. For example, f could be the final model. So basically, in this whole process, they only exchanged encrypted data and they didn't get to see each other's data, but they all get to learn the final model. So that was the cryptographic approach. And now the hardware enclave approach works as follows. So first, at a high level, hardware enclaves are hardware modules that create a hardware-enforced isolated execution environment. Basically, the CPU is protected physically by hardware, and every data that leaves the CPU is encrypted by a memory encryption engine. So everything that goes outside of the CPU is encrypted. And data, when it comes back in, it's decrypted by this memory encryption engine, and then the core of the CPU gets to compute on regular data. So that makes it quite fast. But the nice thing about it is that any software running on this machine, for example, even an administrator with root access on the machine, cannot see anything but encrypted data. The decrypted data only lies deep inside the processor under the die, and there's no way physically to reach there and access the data. It's believed to be very, very, very hard. And from the perspective of the software in the machine, looking to memory, the data is all encrypted. So that's why the enclaves promise a very strong security guarantee. The nice thing about enclaves is that currently they're supported by the major CPU vendors such as Intel, AMD, and ARM. So it's becoming quite widely available. So here's how you would do collaborative learning with enclaves. Each healthcare organization has its own cryptographic key. Then it's going to have to check that the enclaves, let's say they're running in the cloud, are correctly set up. So there's a special process called remote attestation in which each healthcare organization can verify that the enclaves set up in the cloud are actually correct enclaves and are actually going to run the training algorithm that the organizations agreed to run. And this process is an automatic process that would be run on the organization side. The same thing happens. So once this verification is correct, finished, the healthcare organization can share its key with the enclave. Okay, so now each enclave has the key for the data of that organization, so it can decrypt the data of that organization. But again, that key is only deep inside the hardware. It's not available outside of the enclave. It's not available to even a root attacker on that cloud machine. So now the same thing happens for the other two healthcare organizations. They all also do the verification and upload their key in the enclaves. Next is that each healthcare organization encrypts their own medical data with their own key, and then they send it to the enclaves. The enclaves can decrypt it because they have the key, and they can compute on this data inside the enclave. They can run training algorithms over the joint data, the data from all of the organizations together, producing models that then get encrypted and released from the enclave. Okay, so again, the cloud will not even see the model. The model now gets sent back to each of the organizations, and they can decrypt it and benefit from this aggregate model. But during this whole process, none of the organizations saw each other's data, and not the cloud. The cloud also didn't see the data of the organizations. Okay, so now I told you at a high level about the two approaches, cryptographic and hardware enclaves. And my students and I have done extensive research in each one of these approaches. And the reason is that there isn't a winner. There are trade-offs between them. So we've done work in all kinds of computations, such as analytics, machine learning. How do you run them with cryptography? How do you run them with hardware enclaves? So here are some of the trade-offs. The cryptographic approach is nice because it's software only and you don't need specialized hardware. But unfortunately, it's very slow and expensive for complex computation or big data. This is a huge limitation, and at this moment, it is not efficient enough to run realistic training of realistic and common training algorithms on sensitive data in the real world applications. Also, rich analytics is also not currently practical. The overhead is still around 10 to the 6 to, basically 1,000,000 times slower, depending on the application. It's practical though for very, 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 very specific functionalities, but for more rich functionalities like learning of many, training of many algorithms or data analytics, that's too complicated, too complex for these kind of tools to support. Now, on the other hand, enclaves are much, much faster. And they can actually run complex learning and analytics efficiently. So from that standpoint of performance, they can readily be used in practice. But they have some downsides. One is the required trusted hardware. You have to have that setup. Fortunately, that is getting mitigated because now we have confidential computing clouds emerging. Azure is already available with an enclave cloud that people can use. And AWS and Google Cloud are in preview. So the main problem that remains is that enclaves suffer from side channels, which are basically attack vectors through which one can indirectly take data out from the enclave. For example, the pattern of accessing data to main memory. Even if the data is encrypted, just the pattern by which you access the data in main memory could leak some information. So the nice thing, though, is that we can actually combine the cryptographic approach and the hardware enclave approach to try to obtain the best of both worlds, and we've done extensive research in that. So in our works in Opaque, OCQ, Oblix, and Visor, what we do is we compute using the enclaves, but we use cryptography to help us prevent against the side channels. But the computation is still fast because of the enclaves. So in some sense, we managed to recoup the best of both worlds. Our MC² open source implements this dual approach of hardware enclaves and cryptographic fortification. And we have a number of projects that are actively being maintained and that we provide support for. And those are XGBoost, which is a common decision tree library, and Opaque, which is analytics, Spark SQL analytics. So we support this in a private and in a privacy preserving way and collaborative way. And then we have a number of research prototypes, which is our latest research that are exploratory. We also have a number of use cases already. Some companies have used MC² in production or internally, and also some collaborations in the medical sector with NVIDIA. If you have a use case where you'd like to use such a collaborative and privacy preserving technology, then please let us know and try our open source. One request we had commonly from the companies we're collaborating with is the need to provide 24/7 support or sometimes a new feature. And that's, in going beyond just having a research prototype, because we realize that, sometimes one needs to depend on something more mature, more actively developed. So because of this, 3 of my students, 2 graduating with their PhD and 1 with their master's, dedicated themselves to starting a company around open source. And together with our colleague Jon Stojka, who is the co-founder of Databricks, basically providing, maintaining the open source, providing support, offering an easy-to-use interface, and richer learning algorithms for the medical and financial sector. And all of this is released so the open source is released under the permissive license. So in summary, I told you about MC², which enables the idea of sharing without showing. And I explained at a high level how the technology works. The idea is that we combine hardware enclaves and cryptographic fortification, which enables healthcare organizations to put together their confidential data to train better models and make better predictions. And in the process, no organization can see each other's data, and not even the cloud. So it really is sharing without showing. And again, this is open source, so feel free to play with it and contact us if you want to collaborate on your use case. Thank you.
In this demo video, we will demonstrate the life cycle of a disease prediction analysis. We'll have the client, that is a hospital, train a disease prediction model using the MC² platform, running remotely within enclaves on Azure Confidential Compute. The setup for the demo is as follows. We have a client application running on the premises of a hospital. The workings of the client application can be seen in the top screen on the right. We also have a deployment of a cluster of virtual machines on Azure that can read and write to Azure storage, with MC² running within enclaves on these machines. The three screens on the bottom right show the workings of these virtual machines. In the demo, we'll take you through the following steps. First, the user encrypts their data and uploads the encrypted data to Azure storage using the client application. Next, MC² trains a model on the encrypted data within the enclaves and produces encrypted results. Finally, the client downloads the encrypted results, decrypts them, and takes action based on the output. We now start the demo. Step 1. This is what the user's unencrypted training data looks like. This is a breast cancer dataset that we obtained from the UCI repository. Each row in the dataset represents a patient, along with a list of features which includes information such as health history, symptoms, etc. The user's test data, on which predictions will be run, looks similar. The user first executes the command MC² upload. This command automatically encrypts the user's data with a secret key and uploads it to Azure storage from where the server can access it. As you can see, the server only sees the encrypted data, which is indistinguishable from random characters, and cannot decrypt it because it does not have the key. Before starting the next step, the user prepares the script containing the computation that will be run by MC². This is what a regular training script looks like without the modifications required by MC². The script first trains a decision tree model on the training data, and then runs predictions on the test data. To run this script using MC², the user only needs to make one modification. They only need to replace the imported training library with the MC² version. Step 2. We have the MC² software running on the server. In the background, the server launches the software on all the virtual machines in the cluster, creating a single logical entity over the farm of Azure virtual machines, showing the scalability of our solution. During the training process, we can't see any output on the virtual machines, and so we'll instead show you how the CPUs get utilized during training. The user then executes the command MC² run. In the background, the client application automatically attests the MC² deployment on the cloud, making sure that the correct software is running securely within enclaves. It then tells MC² to trigger the training process. MC² loads the data within enclaves across the virtual machines and trains the model on the data using all the machines at its disposal, finally producing a set of encrypted results that it writes back to Azure storage. Once again, the server only sees the encrypted results and cannot decrypt it because it does not have the key. Step 3. The user executes the command MC² download. This command downloads the prediction results from the storage on Azure and decrypts them. The output is actionable by the hospital. In this case, the second column shows the probability of each patient contracting the disease. So, for example, the hospital can have a follow-up process for high-risk patients. That concludes the demo. Thank you for your time.